In the previous video, we posed this problem, second order linear constant coefficient non-homogeneous DE. The solution to the homogeneous part has been the same in all the examples that we've been using. And if you try a solution of that form, you get an equation for A that doesn't have a solution, as we saw in the previous video. The reason that happened is because that function is a solution of the homogeneous differential equation. If that function is a solution of the homogeneous differential equation, it can't possibly be a solution of the non-homogeneous differential equation. It can't possibly work. It turns out the solution in this situation is to multiply by x and keep multiplying by x if necessary until you don't have any more solution of the homogeneous differential equation. There's a little bit of discussion in the text about why that works. So the least you need to know is, in this situation where the right-hand side is a solution of the homogeneous DE, multiply by x until you don't have a solution of the homogeneous DE anymore. So we're going to use that ax e to the 3x for our guess. And the rest of the method is pretty much the same as before. Now for the first derivative, we're going to have to use the product rule. That gives us a e to the 3x plus 3ax e to the 3x. And then for the second derivative, we're going to have to use the chain rule on the first term and the product rule on the second term, which gives us this. So then we take those expressions for y particular double prime, and y particular prime, and substitute those into the original differential equation. At this point, I'm introducing a little bit of shorthand that I like to use in connection with this method, just so I don't have to write e to the 3x all the time. I know there's going to be a lot of e to the 3x's throughout this whole thing, so just to save a little bit of writing, rather than writing e to the 3x over and over again, I'm just going to write e as a little substitution for that. It makes it a little bit easier to write and a little bit easier to see what's going on. So this is the expression we came up with for the second derivative. This is the expression we came up with for the first derivative. Minus 6y particular prime is e to the 3x. Notice that the x terms all cancel out, which was supposed to happen. You have 9ax minus 3ax minus 6ax. So those terms all go away, and you're left with just 6ae minus ae on the left-hand side and e on the right-hand side. And then we divide out the common factor of e, and that gives us the equation 5a equals 1. So a is 1/5. So our particular solution that we came up with is 1/5 x e to the 3x. And our general solution would be c1 e to the 3x, c2 e to the minus 2x, plus 1/5 x e to the 3x. In example 4, we have the same left-hand side, so the same homogeneous part. Now we have cosine 2x for our right-hand side. Of course, when you start taking derivatives of cosine terms, you're going to start having sine terms pop up as well. So for our guess, we'll go ahead and assume something of this form, a cosine 2x plus b sine 2x, to be on the safe side. So that will give us, we'll end up with two equations and two unknowns, a and b. Taking the first derivative of that, we get minus 2a sine plus 2b cosine using the chain rule. And then for the second derivative, using the chain rule again, we've got minus 4a cosine minus 4b sine. At this point, just like before, we're taking those expressions and plugging into our differential equation. And I like to use a little bit of shorthand here, just mainly to save writing. So if C stands for cosine 2x and S stands for sine 2x, this is the expression we came up with for y double prime using my shorthand notation, minus 4ac minus 4bs. This is the expression that we came up with for y prime using my shorthand notation, minus 2as plus 2bc minus 6y particular ac plus bs. And the right hand side is just c. At that point, we have two equations and two unknowns, which we get by matching the coefficients of C and S on the left side and right side. So the coefficient of C, the cosine terms on the left side, is minus 4a minus 2b minus 6a, and the coefficient of C on the right hand side is 1. The coefficient of S on the left hand side is minus 4b plus 2a minus 6b, and the coefficient of S on the right hand side is 0. So solving that last equation, 2a is 10b, so b is a over 5. A little bit of arithmetic here, and then we take that and plug that into the cosine equation, which gives us this, minus 10a minus 2/5 a equals 1, which gives us a is minus 5 over 52 and b is 1 over 52. So our particular solution, taking those values of a and b back, our particular solution is minus 5 over 52 cosine 2x minus 1 over 52 sine 2x, which agrees with Wolfram alpha. Finally, here's an example where we wrap up the process by solving a problem where we have two initial conditions. It's the same differential equation that we've seen before, same left-hand side. So we have that homogeneous solution, and we came up with our particular solution in an earlier example. So the only thing left to do here is to plug in our initial conditions, which will give us two equations and two unknowns for C1 and C2. So here's our general solution, and here is the derivative of the general solution. So plugging in 0 into our general solution, we get this equation. So C1 plus C2 plus 1/9 is 8, plugging in 0 into the derivative equation, we get 3c1 minus 2c2 minus 2/3 equals 0. So that gives us these two equations for C1 and C2, where we have multiplied the first equation by 2 on both sides with a view toward eliminating C2. If we just add those two equations now, we'll have C2 eliminated, and then 5C1 minus 4/9 is 16, which we then solve. You're probably going to want to use a calculator for some of these calculations. So C1 turns out to be 148 over 45. And then we take that value and plug back into what we had originally for our top equation. Plugging that value in that we just found for C1, we get that equation for C2, which we solve and find C2 is 23 over 5. So putting everything together, plugging in the values of C1 and C2, that is our particular solution of our initial value problem, the homogeneous part with the values of C1 and C2 that we just found, and the particular solution. So there's no more unknown parameters, and that function will satisfy the non-homogeneous differential equation, and it will satisfy both initial conditions. And that does agree with the solution in Wolfram alpha of that initial value problem. So quick review of the method. For a non-homogeneous DE, the first thing you always want to do is find the solution of the homogeneous part. Once you've done that, you find the solution of, you find a particular solution. Remember, when you're finding a particular solution, you don't want to assume a particular solution that is actually a solution of the homogeneous part, because that's never going to work, as we've seen. So find your homogeneous solution, then find your particular solution, and then if you have some initial conditions given as well, as we saw in example 5, we take our general solution and use the general solution and the given initial conditions to determine the values of C1 and C2.